So in the last video, we looked at this rental car model, and we made some observations about the fixed points and the stability. And so I want to summarize those for a minute, and then we'll look at another example. So the first thing we noticed is that the transition matrix had an eigenvalue of 1 with an eigenvector, which we argued was the fixed point of the system. And that's not a coincidence. That's always going to be true of a Markov chain. And you can prove that based on the fact that the probabilities that make up the matrix always sum to 1. And so it takes a little bit of linear algebra to prove it, but you can actually show that indeed there's always going to be the eigenvalue of 1. And that eigenvector is going to be a fixed point of the system, since that just means that the new state is equal to a times the old state. All right, we can also say something about stability of that fixed point. First of all of the eigenvalues of a Markov chain, again, you can prove this, are going to be less than or equal to 1. And so there's really two possibilities. If all of the other eigenvalues are less than 1, then you can show that that fixed point that we found before is going to be stable. And again, that fixed point only makes sense if the entries sum to 1, so we should say the normalized eigenvector is the fixed point. On the other hand, if one of the other eigenvalues is 1 also, or at least its absolute value is 1, then potentially we're going to have more complicated behavior. One of the possibilities is that the system could oscillate forever. Alternatively, you could have multiple stable states where you just stay. And so either of those would correspond to a neutrally stable fixed point. The one thing you cannot have in a Markov chain is an unstable fixed point, and that's due to the fact that these values represent probabilities. You can't have probabilities going off to infinity. They have to stay between 0 and 1. And so the eigenvalues will never exceed 1. All right, so that's something to have in the back of your mind. Fixed points can be found by finding the eigenvector corresponding to an eigenvalue with absolute value 1 for a Markov chain. All right, let's look at an example. Let's suppose that the probability that it's sunny tomorrow, given that it's sunny today, is 0.9. And the probability that it's rainy tomorrow, given that it's sunny today, is 0.1. And similarly, that if it's rainy today, there's a 50% chance it's going to be rainy tomorrow, but there's also a 50% chance that it's sunny. Okay, so that describes a Markov chain because there's two states, rainy and sunny, and the probabilities for the future depend only on the current state, not on the past. And we can write down, therefore, a nice transition matrix to describe that. Notice if we think about the columns as the last state, we have two columns, one for sunny and one for rainy. So that's today. And then for tomorrow, we can have two rows, sunny and rainy. And so we can just write our probabilities in that matrix in the corresponding location. And you see that the columns must sum to 1 when you do this, since when you leave the sunny state, you always have to go somewhere, and same thing for the rainy state. All right, so we've got a transition matrix. Here our state variable we can think of as representing sunny and rainy, and both of those are probabilities. Okay, so we have the probability of sunny as the first component and the probability that it's rainy for the second component on day n. And if we start on a sunny day, then the initial state would be 1, 0. If we start on a rainy day, the state would be 0, 1. And we can write down a nice analytical solution for xn in terms of the initial state by multiplying by the matrix A n times. All right, so our goal is going to be to answer a couple of different questions about this system, ultimately building towards this steady state solution. So the first question is, suppose that today is Sunday, or suppose that today is Friday, rather. We want to know the probability that it's sunny on Sunday. And so essentially what that's saying is if it's sunny today, then the state is 1, 0. We want to know what is the probability in the first row for x2. That's what we want to find. We want to know the probability that corresponds to being sunny after 2 days, since Sunday is obviously 2 days after Friday. Okay, so let's do that. First thing we can do is, given the transition matrix, we can find the probability distribution for Saturday. And then once we've got that, we can multiply by A again to get the probability distribution for Sunday. And if you multiply that out, you'll end up getting 0.86 and 0.14 roughly. And so that would mean that there's an 86% chance that it's sunny and a 14% chance that it's rainy 2 days later. Okay? Now, if we change the question so that instead of going from Friday to Sunday, we go from Friday to Friday, then that's a 7-day period. And we can take that same approach. The only difference is we'll multiply by A not twice, but rather 7 times. And in that case, you'll see that the probabilities approach 0.83336 and 0.1664 after 7 days. And at that point, given that it hasn't changed much, you might conjecture that maybe we're close to a fixed point. And so let's actually compute a numerical solution to check that. And you see that yes, indeed, as you multiply by A over and over again, you're actually approaching the solution 5/6, 1/6. At least that's what the numerical solution suggests. But are we sure that's the exact value? How do we know? Well, this is where we can use fixed points and stability analysis to check. And so what are the fixed point of this model? Well, if the model has the form xn plus 1 equals axn, then the fixed points must satisfy x star equals ax star. Or we can think of that as 1 x star equals ax star. So we need the eigenvalue or eigenvector with eigenvalue 1. And so we can either do that by just computing all the eigenvectors and looking for the one that corresponds to eigenvalue 1, or another way to do that is you could rearrange this equation and write it as, you can think of that as I times x star minus A times x star equals 0, which is equivalent to saying I minus A times x star equals 0. And we could try to solve that linear system of equations as well. Both will give you the same solution. I'll go with the first approach. Let's find the eigenvalues and eigenvectors. All right, so our matrix was, we had 0.9, 0.5, 0.1, 0.5. And we'll compute the eigenvectors and eigenvalues. And we see that the eigenvector 1 that corresponds to 1 is the first column. So I'll call this x star is the first column. And let me extract that. So we'll take all rows in column 1. And now let's save an x star. But you'll notice that doesn't make sense as a solution here because in a Markov chain, the state variable represents probabilities. And therefore, well, that can't be right because the probabilities don't sum to 1. So what can we do? Well, we wanted to normalize that vector. And so I'll define x star to be what I have right now divided by the sum of the entries. And notice that all that does is it shrinks both values proportionally, and you get down to 0.8333 and 0.1667. And you could actually do this by hand so that it's not just a decimal estimate. And you'll see that if you plug in 5/6, 1/6, it does indeed satisfy that. And so let's check that. If I do 5/6, 1/6, I'll go back to my slides here. The claim is that should be equal to 0.9, 0.5, 0.1, 0.5 times itself. And so we will get, let's see, this is just 9/10. So 9/10 times 5/6 plus 5/10 times 5/6 in the first row. And then 1/10 times 5/6 plus 5/10 times 5/6. And if we multiply that out, we're going to have, looks like 45. Did we do that right? Oops, let's do that a little more carefully. When we multiply out, that should be a 1/6 for the second product. That looks a little better. If you multiply that out, we have 45 over 60 plus 5 over 60. So that's 50 over 60 in the first row. And then the second row, we have 5 over 60 plus 5 over 60, so 10 over 60, which simplifies down to 5, 6, 1, 6. So that does indeed check out. Okay, so hopefully between those couple of examples, you've got the basics of Markov chains down. We can apply all of our techniques from the earlier part of the semester where we looked at dynamical systems, and that means using fixed point and stability analysis. The only difference is Markov chains are a little more predictable since the state vector and the transition matrix all represent probabilities, and so we can say a little bit more about what's going to happen. All right, we'll stop there and continue in the next batch of videos.